Now let us look at the reactions of pyridine. Electrophilic aromatic substitution reaction. In this section, we'll ask ourselves three questions. Question number 1. Why is it that pyridine undergoes electrophilic aromatic substitution reaction only under vigorous conditions? Question number 2. At which position does electrophilic aromatic substitution reaction takes place for the pyridine ring? And question number 3. What are the examples of electrophilic aromatic substitution reaction in the pyridine ring? Question number 1. Why is it that pyridine undergoes electrophilic aromatic substitution reaction under vigorous conditions? There are two reasons for this. Reason number 1, presence of an electronegative nitrogen atom. Reason number 2, presence of a lone pair of electron on the nitrogen atom. Let us look at reason number 1, presence of electronegative nitrogen atom. Pyridine is an aromatic sextet consisting of 6 pi electron. It is this 6 pi electron that makes the pyridine ring susceptible to attack by an electrophile and thus undergo electrophilic aromatic substitution reaction. However, this reaction does not take place easily for pyridine. It takes place under vigorous conditions. But why is it so? To know the answer, we need to introspect the structure of pyridine. Pyridine has 5 carbon atoms and 1 electronegative nitrogen atom. It is this electronegative nitrogen atom that pulls the adjacently lying electron pair towards itself, and that makes an adjacently lying carbon atom positive in charge. What follows next is a cascade of electron pair transfer, which results in a positive charge at the ortho and the para positions. That is, in other words, the nitrogen atom pulls an electron pair from the pyridine ring, thus resulting in a great electron deficiency in pyridine ring. This makes the pyridine ring very unattractive to an electrophilic attack, and thus it is very difficult to initiate an electrophilic attack on the pyridine ring. Reason number 2, presence of an lone pair of electron on the nitrogen atom. If you ponder, you would wonder, why would the electrophile attack an electron pair that is delocalized? Rather, it is much easier for an electrophile to attack an electron pair that is localized on the sp2 hybrid orbital of the nitrogen atom. It attacks the localized pair of electron, resulting in the formation of a pyridinium cationic salt. The formation of pyridinium cationic salt is favored because the salt is stabilized by resonance. It is the cumulative effect of these two reasons that brings down the reactivity of the pyridine ring towards an electrophile. However, electrophilic substitution reaction is still possible in pyridine ring under vigorous conditions. Question number 2. At which of the position of the pyridine ring would the electrophile attack under vigorous conditions? That is, whether the electrophile would attack at position 3 or position 2 or position 4. To know the answer to this question, one has to compare the stability of the intermediate cations that are formed by attack of the electrophile at the third, at the second, and at the fourth position. Let us first look at the intermediate cation that is formed by the attack of an electrophile at the C3 position. The intermediate cation formed is a resonance hybrid structure of three contributing forms. To restore neutrality, an H plus is eliminated and the electron pair that is shared with H is taken in to form 3 substituted product. The same applies for attack at C2 and attack at C4. Structure A and structure B resulting from attack of an electrophile at the C2 and the C4 position respectively are nonsensical structures. That means structure A and structure B would never even form at the very first place. Why? Because these structures are high energy structures or they are very unstable structures. The reason of this is that the nitrogen atom in these structures are unstable. The nitrogen atom in these structures have only 1, 2, 3, 4, 5, 6 electrons in its valence shell. Here too, the nitrogen atom has 6 electrons in its valence shell. If you exclude these structures and look at other structures, be it from an attack at C3, C4 or C2 positions, other structures have a nitrogen atom in which the nitrogen atom has 8 electrons in its valence shell. Look at this: 1, 2, 3, 4, 5, 6, 7, 8. If you look at other structures, all other structures have 8 electrons in its valence shell. The nitrogen has 8 electrons in its valence shell, and thus the nitrogen has achieved the inert configuration of neon in these structures. That is not the case with structure A and structure B. It is for this reason that structure A and structure B have minimum contribution towards the resonance hybrid structure of the intermediate cation forms for attack at C2 and C4. Such is their contribution that their contribution is regarded as nil. That is to say that the resonance hybrid of the intermediate cation for attack at C2 is a resonance hybrid structure of these two, and the resonance hybrid structure for the intermediate cation by attack at C4 is a resonance hybrid structure of these two. On the other hand, the resonance hybrid structure is a combination of 3 resonating structures for attack at C3. Thus, the resonance hybrid structure of the intermediate cation at the C3 is more stable than at the C2 and the C4 position. Therefore, the attack at C3 position is preferable and it is the 3 substituted product that predominates. In case the third position is filled, attack would take place at the other available beta position relative to nitrogen atom, which is 5th position. Question number 3. What are the examples of electrophilic aromatic substitution reactions of pyridine? Example number 1. Nitration of pyridine. Pyridine, when it is treated with nitrating mixture, which is an equimolar proportion of potassium nitrate and H2SO4, under vigorous conditions undergoes nitration to form 3-nitropyridine. Mechanism: electrophilic aromatic substitution reaction has 3 steps. Step number 1 is the formation of electrophile. Potassium nitrate reacts with H2SO4 to form NO2+, which is also called as the nitronium ion. Nitronium ion is the electrophile in the reaction. In step number 2, it is this NO2+ that attacks at the most favorable position, which is position 3, and that attack leads to a resonance stabilized intermediate carbocation. In step number 3, an H plus from the third position is knocked out by OH minus, which is a very strong base that has been produced in the step number 1. This same base deprotonates the H plus from third position. Simultaneously, the electron pair that the pyridine had shared with H plus is pulled in and to restore neutrality as well as to restore resonance, and yielding the product 3-nitropyridine. Now, usually in benzene, we are using HNO3 and H2SO4 as nitrating mixture, which yields the nitronium ion. Here, we have used KNO3 in place of HNO3 to yield the same nitronium ion. But why? Why KNO3 in pyridine? KNO3 interacts with H2SO4 to yield a strong base, which is OH minus. Had we used HNO3 in place of KNO3, then HNO3 would have interacted with H2SO4 to yield a mild base, which is HSO4 minus. In this reaction, we actually require a strong base like an OH minus. The strong base, it can attract proton from third position with much greater intensity, and that would increase the electron density at the third position. NO2 plus would now be attracted at a much faster rate. When there is a greater electron density at third position, NO2 plus would be attracted much faster. So the reason why we have used KNO3 is to increase the rate of electrophilic aromatic substitution reaction. Even though we have used KNO3 to increase the rate of reaction, and even though the reactions of the conditions are vigorous, the yield of the 3-nitropyridine is very poor. It is only 8%. Example number 2. Sulfonation of pyridine. Pyridine on treatment with fuming H2SO4 in the presence of the catalyst mercuric sulfate and under heat undergoes sulfonation to yield pyridine 3-sulfonic acid. Mechanism: electrophilic aromatic substitution, which has 3 steps. Step number 1, formation of electrophil. Under fuming condition, one molecule of H2SO4 reacts with another molecule to produce sulfur trioxide. The molecule of sulfur trioxide exhibits resonance. It has 3 resonating structures. In all of these resonating structures, the negative atom is with each of the oxygen atom. Positive charge always rests on the sulfur atom. Therefore, it is a sulfur atom of the sulfur trioxide which acts as an electrophil. In step number 2, the sulfur atom of the sulfur trioxide attacks the most favorable position of the pyridine ring, which is position number 3, to produce an intermediate carbocation that has been stabilized by resonance. In step number 3, the HSO4 minus that was released in step number 1 acts as a base, a mild base, and knocks out a proton from position number 3. At the same time, the electron pair that the pyridine ring shared with that proton is pulled inside, and thus the neutrality as well as resonance of the pyridine ring is restored as it was in the beginning. It is good to remind ourselves that the oxygen of sulfur trioxide is still negative. It has a pair of electrons and thus acts as a Lewis base, ready to donate electron to any incoming acid. An acid is present here in this reaction. It was released in step number 1. It acts as an anhydrous acid because it can emit H plus from H2O. Therefore, it emits H plus. The H plus emitted H plus acts as a Lewis acid. It can accept a pair of electron, and it accepts a pair of electron from SO3 to become SO3H, and thus the formation of pyridine 3-sulfonic acid. In the reaction of sulfonation of pyridine, we use the catalyst mercuric sulfate. Nitrogen is electronegative. It pulls an electron pair of the pyridine ring. Thus, causing great electron deficiency in the pyridine ring. Mercury of the mercuric sulfate is electropositive in nature. When it is in the near vicinity of pyridine, it pumps its electron to the pyridine ring. Thus, it somewhat counterbalances the electronegative effect of the nitrogen atom because it is electropositive. Therefore, the electron density of the pyridine ring is somewhat maintained when HgSO4 is in the near vicinity of pyridine. This increases the attraction of the electrophile SO3 plus towards the pyridine ring. That is, the presence of HgSO4 actually increases the rate of electrophilic aromatic substitution reaction, thus establishing the role of HgSO4 as a catalyst. Example number 3. Bromination of pyridine. Vapors of pyridine and bromine pass through activated charcoal to yield 3-bromopyridine. If the vapors of 3-bromopyridine persist over charcoal along with the vapors of bromine, then bromine would react with 3-bromopyridine to yield 3,5-dibromopyridine. Mechanism: electrophilic aromatic substitution. It has 3 steps. Step number 1, formation of electrophile. Unlike UV rays, which can bring about homolytic fission of bromine, heat from charcoal brings heterolytic fission. That means one of the atoms in the molecule of bromine gets the pair of electron. The one that gets becomes negative. The one that loses the pair of electron is positive and is the electrophile. In step number 2, the electrophile Br positive attacks pyridine ring at the most favorable position, which is position number 3. For when it attacks at position number 3, it can get an intermediate carbocation having 3 resonating structures, and this is the intermediate carbocation. In step number 3, the Lewis base that is formed in step number 1 now knocks out a proton from 3rd position. Simultaneously, the pair of electron that the pyridine shared with that proton is pulled in, thus restoring the neutrality as well as resonance of the pyridine ring and forming the product 3-bromopyridine. In the bromination of pyridine, the catalyst that is used is charcoal. Charcoal gives the necessary energy in the form of heat to break up these bonds. When these pi bonds are broken, the electron density at the 3rd position increases. This attracts the bromine instantaneously, and the bromine positive attacks the pyridine ring to give the substituted product. Therefore, charcoal increases the rate of electrophilic aromatic substitution reaction, thus reinforcing the role of charcoal as a catalyst. Pyridine does not undergo Friedel-Crafts alkylation or Friedel-Crafts acylation. This is because the Lewis acid catalyst, which is AlCl3 or FeCl3, does not wait for electron pair from alkyl halide in case of Friedel-Crafts alkylation or acyl halide in case of Friedel-Crafts acylation. Instead, the Lewis acid catalyst coordinates with the lone pair of electron on nitrogen to form pyridine aluminum salt if AlCl3 is involved, or pyridine iron salt if FeCl3 is involved. Dear students, I hope you have liked and you have understood the class. If the class was helpful for you and if you have liked it, please do not forget to like, share and subscribe this channel. Thank you very much.